tardes, ¿puedo escucharme? Okay, voy a hablar en inglés porque es mi idioma primario. So I'm going to be talking about hydroponics and controlled environment agriculture. This is a picture from our research farm in Barranquitas, 20 minutes in Barrio Quebradilla. So what is hydroponics? So hydroponics is the soilless water culture of plants, meaning we grow without soil, so sin la tierra. And it comes from the words meaning hydro is water, and ponos, which is work or labor. So this means water working. So hydroponics, the idea is the water is working so the farmer can work less. Not always the case. So the history of hydroponics and the idea has been around for centuries. Some examples are the Hanging Gardens of Babylon in ancient Mesopotamia, and they used water with a screw called the Archimedes screw that brought water all the way to the top of a pyramid from a local stream, and then it worked its way down these channels to water plants in this garden. Also, there are floating gardens where indigenous peoples used local lakes or rivers or built their own systems with rafts, sometimes made out of reeds or grasses, and grew plants on the sides of them or inside of them. So this is a picture of the chinampas, which were these floating gardens that the Aztec built in modern-day Mexico. So they used hydroponics. They had fish. It's actually aquaponics. They used the fish, and their poop acted as fertilizer for the plants, the maize and the trees that grew next to these streams. But now we use it in modern day. It came out of research trying to figure out what were the necessary ingredients that the plants need. And ultimately, researchers figured out the certain elements that are essential for plant growth, and they were able to grow plants without soil. So when you see hydroponics, this is what you see. Los raíces. You see the roots. So these are different hydroponic systems. Most of them are a term called deep water culture. I'll explain more on that later. But you can see hydroponics consists of three main things. The soil-less media, so growing in a media without soil, a nutrient solution, which is made up of water and essential nutrients, and aeration. So somehow we need to create movement in the water with an air stone or dissolved oxygen injected or some kind of waterfall to allow there to be oxygen in the water, which the plants need as they grow. If they don't have oxygen, they'll turn brown and they'll die. So first, we'll go through what is a soil-less media. So something has to hold the plant. The plant can't just grow in water. It will sink, it will fall. It needs to grow in something. So what we use is a soil-less media. So here's a picture of one of the plants at our research farm, and it's growing in a floral foam. So this is a media that is not soil. It's ultimately made from some kind of plastic derivative, and it's like a sponge. So it's porous, there's holes, little air holes in it, and you plant the seed and you water it, and it holds water, and the roots can grow down into it, and then the plant is supported. So it's sterile, meaning there's no microbes, there's no pathogens, but there's also no beneficial microbes. It's inert, which means there's no nutrients in it, there's no chemical charges, it does not have acidity, and it's not alkaline, it's neutral. It has water holding capacity, so when you water it, it can hold water and keep the plant moist and living. And it also has air holding capacity. So like a sponge, there's little holes in it, and those hold air so that the roots, as they're growing, they can have air to take up when they do respiration and grow. So what is the best hydroponic growing medium? Well, there's a lot of debate on this, but there's a couple different types. So let's see if this pointer works. Okay. So what you're seeing, there's two different classes. There's inorganic and there's organic. So there's a lot more inorganic medias. What those are like the floral foam is inorganic. It's made of plastic. This is called rock wool, which is made out of superheated rocks, and it's spun at very high temperatures, almost like cotton candy, to make this sponge kind of material. But it's made of rock, so it's not organic. They use this a lot in the Netherlands, where hydroponics has kind of been pioneered in its modern day form. Rocks like this, or pebbles, those are inorganic, but they can hold the roots. Clay pebbles, which are clay that have been heated and baked, they can hold the roots. This is vermiculite, and these are another type of rock that are kind of popped like popcorn, and they form a structure that holds water and also holds air. All of these, they don't have any living material in them. Then there's organic, which has living material in it. So peat moss, I don't have it pictured here, but that's an example that most, if you buy at the grocery store, like let's say you want to buy peppers or cacao for your house, and you buy it in a pot. The black media that it's growing in that pot is peat moss. So that is an organic material that's normally mined from large bogs that are up in Canada, and so it's shipped and it's blended and it's mixed with things like vermiculite and perlite to add extra air holding capacity. And that's widely used, but it's not the most sustainable because we're mining it from the ground. Then there's cocoa coir, which is made from the husk of coconut shells, and a place like Puerto Rico where there's lots of coconuts and palm trees, that's a really great medium because we can use it, we can use something that's local, we take it, we shred it, but there's problems with that because they grow next to the ocean. All of the salty water from the ocean can get in to that coconut husk. And then when we try to grow the plants, it's super salty, and the plants don't like salt, and they can die. So it has to be manufactured properly to be able to be free of those salts and other products. And then rice hulls like this is where you take, this is another husk of like rice, and these are taken and they don't really have much nutrition in them. They're kind of just a waste product, and they're used, again, to hold the roots and support them. So the next part of the equation of hydroponics is about the nutrients and the pH. So there are things called macronutrients, which are needed in high concentrations. So these are the first six: nitrogen, phosphorus, potassium, sulfur, calcium, and magnesium. They're needed in large concentrations for the plant, primarily nitrogen, phosphorus, and potassium. If you ever buy fertilizer for your house plants or around your garden, you'll see it says NPK. So those fertilizers stand for nitrogen N, P for phosphorus, and K for potassium. Those are needed in a high concentration. And then the micronutrients, these are like these other minerals, such as iron and manganese, boron, copper, and zinc, and molybdenum. They're needed in a lot lower concentrations. They're needed for growth. If the plant is without iron, for instance, it'll turn yellow and it won't grow as fast. Or if it's, if there's no molybdenum, it can grow all distorted. So we need all of these. These are all essential nutrients, but they're needed in different concentrations. So when you're growing in hydroponics, you have to provide all of these nutrients for the water and for the plant. Because in soil, they're already there. But in water that you're taking from your faucet, you have to mix these in or the plant's not going to grow properly. The next step is about pH. So pH has to do with the acidity of the solution. So you can see on this chart, this is showing the optimal uptake of these nutrients. So where it's thick, the plant is able to absorb a lot of it. But where it's thin on the edges, the plant, it's not available for the plant. So you can see the area where all of these are kind of the thickest together is about 6.5. So for plants, we like to say that the optimal pH is between 5.5 and 6.5. So 7 is regular water. Neutral water is normally a pH of 7. So then you add these nutrients and, you're not going to get enough iron and you're not going to get enough manganese. So you have to add in some kind of acid. So it could be phosphoric acid, which you can buy. It's called pH down for hydroponic systems. You can buy sulfuric acid, which is similar to battery acid. You could even use lemon juice, citric acid, to bring down the acid to get it into this optimal range. So now I'm going to go through a couple of the growing systems that are common in hydroponics. So this, again, this is what we have at our research facility. This, where you can see the roots and the plants in water, is what's called deep water culture. So deep water culture is where you have a large body of water of this nutrient solution, and you have these normally styrofoam raft boards that the lettuce is planted in. The little cube that it's first seeded in is planted into these floating rafts, and the roots hang down into the solution, and you have a pump that pumps water through, recirculating those nutrients and adding in oxygen so that the plant roots constantly have nutrients flowing over their roots, they have the oxygen, and they can grow. So this is kind of the simplest way. And this is what it looks like on a large scale system, but you can use this in practice down to even a small bucket scale. You can have a little 1-gallon bucket with a plant and an air stone and nutrients, and you can grow a beautiful head of lettuce. And we're going to do a workshop with that in the greenhouse later today. The next is called nutrient film technique, NFT, or gutter systems. So this is how most of the lettuce that's local and cilantro that's local to Puerto Rico is grown in these gutters that can be made of, just PVC tubing, or they can be bought in like a big system, and you just have some kind of little spaghetti tube, this black tube that puts water and recirculates it on one side of the system, and then it floats down, these are on a slope by gravity, into like a trough where all the water is collected, and then it goes down to a bucket at the end, and a pump pumps the water back to all of these. Now, this uses a lot less water. It's a film. So it could be just less than a half an inch of water floating down, and the media cube soaks up that water, and the plant grows its roots inside of this channel. This is really only good for things like leafy greens and lettuce that have smaller root systems, because you can imagine it's going to get crowded inside of this little pipe if they have big roots. The next is what's called a rock wool or slab culture. So this is for bigger rooted plants like tomatoes, or these are cucumbers. So this is where you take the rock wool, which is this inorganic media, and you can put it inside of a larger cube, and then those cubes are put on top of even larger cubes of rock wool. All of these soak up water like a sponge, and there's little drip emitters here that, again, these little spaghetti tubes that deliver the water from a pump to all of these plants. And so what you can do is you can grow really big plants with very small root systems. And this is how most of the tomatoes are grown in Mexico and in Canada. Actually, Mexico and Canada have a much more developed controlled environment agriculture system than the US or Puerto Rico has, mainly because they've developed these kind of systems and they didn't necessarily have the best growing conditions. For instance, Canada, it gets too cold in the wintertime, so they need to build these large greenhouses. And in Mexico, it's so hot and the soil dries out so quickly, they need to have this kind of hydroponic irrigation to keep their plants growing. So this is a system called high wire production. So what you have is you have a wire that runs all the way to the roof of this greenhouse. Now these greenhouses can be 18 to 21 feet tall, or 6 to 7 meters. So the plants can grow 6 to 7 meters tall. And it's tomatoes, peppers, eggplants, cucumbers. They're what are called vine crops. So this kind of grows as a vine, and the tomatoes grow off of it. And you can see the bottom leaves are removed, they're thrown onto the ground, and the top of the plant just keeps growing. And they're grown with this drip irrigation that puts in a little bit of water multiple times a day. So these plants have really small roots, but they are very large plants. And this is only achievable in hydroponic systems where you water so frequently. So then another type which is gaining popularity is for strawberries. So this is some research I did at Cornell doing strawberries in substrate culture. So this is what it looks like on a commercial scale, where you have a lot of strawberries growing in this mix. This is a mix of vermiculite and perlite, which are two inorganic substrates. A lot of times they also mix peat in there, so now you're mixing the organic and the inorganic. And again, it's a similar thing. You have these drip tubes that apply the irrigation water, and it runs down to water all of these plants. So there's some pros and cons for hydroponics. The benefits, it allows you to grow where there are poor soil conditions. So you can grow anywhere in the world. They're doing hydroponics in Antarctica at the research station there. They're doing hydroponics in outer space on the space station. They're doing hydroponics on islands in the middle of the Pacific that don't have good soil. So whenever you have these conditions that are hard to grow in, hydroponics makes a lot of sense. You have more control with hydroponics. You can precisely deliver the water and nutrients that a plant needs exactly when it needs them. So what that means is you're able to grow these plants with a lot less water and with less nutrients more efficiently, and the plant will grow faster. So you can get higher yield and higher quality than you would grow out in the field if, for instance, you had a nutrient deficiency in your soil, or your soil was too much clay and there wasn't enough aeration and the roots were getting disease. So you can do a higher quality product faster in hydroponics. So you get better use of the water, the fertilizer, and there's more control points to reduce disease and pests. However, there's some difficulties. So it requires more attention than growing in soil. What happens if you lose power? If the power goes out and you have one of these systems with a big plant with small roots that needs to be watered many times a day, if your power's out, you have no generator, you're not getting water to that plant. Now the plant is going to dry out on a sunny day in a matter of hours, as opposed to out in the field where it has larger roots, the field soil holds more water. So that's one of the risks of hydroponics. If the technology fails, oftentimes you can lose the plant. Also, you can have root diseases that can spread a lot more quickly. So because you have water going to the same plants and you're recirculating that water a lot of the time, if one of the plants gets a root disease, now you've spread it through the irrigation water to all of the plants. And that's a challenge. It's also expensive. All of these pumps, the more advanced the system, the more expensive it's going to be. The NFT system that I showed you before with the PVC pipes, that's probably the lowest cost system that you can build. It's also difficult to grow anything organically with hydroponics. When you start trying to think about organic, now you need to take, cow manure or some other type of fertilizer source that's organic, compost, and mix it into your water. Well, that's going to start to clog those little spaghetti tubes, and it's going to create biofilms that gunk up the pipes, and you can't necessarily deliver all of those essential nutrients to the plants. So most hydroponic systems are inorganic. We use chemical, salt-based fertilizers. So now I want to overview kind of agriculture worldwide and compare it to hydroponics and controlled environment agriculture. So currently about 70% of the world's water consumption goes to agriculture. And 1/3 of all of the world's greenhouse gas emissions go to agriculture. You can see using a big combine and tractor like this requires a lot of fuel, requires a lot of fertilizer, a lot of pesticides when you're growing the same crop on hundreds of hectares. It produces nitrous oxide, which is a greenhouse gas along with carbon dioxide, transportation to bring that agriculture to your grocery store, to your house, and a lot of deforestation, cutting down trees to make room for more agriculture. We're seeing a lot of that in places like Brazil, where they're cutting down parts of the Amazon to grow more soya and maize for feeding animal agriculture. So what is controlled environment agriculture? So this is an innovative method of growing plants to create optimized aerial root zone environments. So this can have higher plant quality, predictable crop timing, and consistent availability, quantity, and hopefully reduce the environmental impact. So what is controlled environment agriculture? It's all about this word, control. So we're trying to control the environment, the air temperature, the light, the carbon dioxide, the relative humidity. All of that is supposed to be optimized and made to the same level all year round so that the plant never has any interruptions. Oftentimes it's grown in hydroponics. Optimal nutrients, optimal pH, optimal oxygen, keeping the temperature of the roots the same. And a lot of automated processes we're starting to see. Automated seeding machines, transplanting machines, harvesting machines, and packing machines. Robots can do a lot of this work, and this is a way that hydroponic growers in controlled environments reduce their cost, which the highest cost is often labor. So here you can see how much lettuce, how much more lettuce you can produce per year in pounds in hydroponics and in greenhouses compared to the field. So you're able to produce 15 to 21 times more lettuce per unit area by growing it one cycle after another cycle at the perfect environmental temperature versus only getting a few rotations per year. So there's different types of controlled environments. There's things called high tunnels, which are low cost. This is just a greenhouse roof structure, maybe a screen to keep out insects, and they're limited or no electricity. Maybe you have some fans. It's pretty inexpensive, only $2 to $5 per square foot. Then you go a step up and you get to greenhouses. So these are normally built out of glass or plastic. They're often heated in northern climates. They have more electricity. There's often supplemental lighting, year-round production. These cost a bit more, like $50 per square foot. And then you have vertical farms, which these are also called plant factories. So this is Aero Farms in New Jersey, and you can see they have level upon level. They aren't using any of the light from the sun. It's all artificial lighting. So in this, you have to have lighting, you have to have HVAC, cooling, and you can see you have complete control over the climate, but it becomes $200+ per square foot, which is really expensive. So you can see global CEA production value. It's projected to be almost a little more than $35 billion in 2024. And there's a lot of opportunity to grow things like tomatoes and lettuce and peppers. And the climate perspective, it's more sustainable. So you can see here that there's a little bit less, these are a little bit complicated. I don't think I have enough time to go through them, but you can see water, it's better. They're using a lot more water in the field than they do in the greenhouse. Can we do it? Normally in rural areas, because land is cheaper, energy is cheaper, labor is cheaper, but transportation cost is a little bit more. So this kind of breaks that down, that this is the cost of field, and this is the cost of growing in controlled environment. It's a lot more. There's a couple barriers to CEA, controlled environment agriculture. The main ones are accessing capital, so making sure that you have enough money to build these projects. If you're building a large commercial greenhouse, it's going to cost millions of dollars, and that's a lot of money to put up front. Making sure you have markets to sell it, making sure you have enough energy to supply the project, making sure you have enough labor to do all of the operations, finding an educated head grower. Again, this idea of making sure we have the people that have the expertise to do the precision agriculture, and making sure that the growing environment is fully controlled and that there's no gaps or spaces where it's too hot or too cold or there's not enough light and you're not maximizing your productivity. So anyway, this is my contact. I don't know if we have any time for questions, but you can email me later. Thank you guys so much.